Okay, so we will continue our chapter 4. Okay, and last time we mentioned about there are two functions called one is we are talking about potential flow. Okay, so the potential flow mean is potential flow. Potential means incompressible, invisible, irrotational. So Gaussian equation reduced to Laplace equation. Okay, so this phi is our so-called velocity potential, and we also introduce so-called stream function. Okay, this is stream function, and stream function definition is like this. This is also automatically satisfy our continuous equation. Okay, this is in the Cartesian coordinate. This is for the polar coordinate. Okay, so once we define the velocity potential as well as our stream function, okay, so we can define so-called complex potential. Okay, this is complex potential. Our Fz is equal to our phi plus I psi. Okay, now this is our velocity potential, and the imaginary part for this complex potential is our stream function. Okay, so this is a complex potential, and z can be defined as x plus iy is a complex variable, and in Cartesian coordinates is equal to r ei theta. Okay, and here we have to define when you deal with the complex function. Okay, for example, fz is a complex function, right? This is a real part, this is imaginary part. This is okay. So for the complex function, okay, fz, if this complex function is an analytical function, okay, in mathematically, the definition of analytical function is what? Is that df dz is independent of direction, which we should calculate. That means, okay, you can calculate this df dz, okay, by any direction. Okay, I can show you later. Okay, what does mean? Okay, for example, okay, when you calculate df dz, okay, and df dz can be in the x direction, so become partial f partial x. This is along the x direction. Okay, we just calculate in specific direction x, and if you calculate like this, so this is our complex potential is equal to partial phi partial x plus partial phi I plus partial psi partial y. Okay, so this is from the x direction. You also can calculate from the y direction. From the y direction here is iy here, so it become partial f partial iy. I mean the vertical direction. Okay, so if you do that, okay, similar thing you can find out that if you do that to the partial f partial y and times divided by I here, you can get this. So any direction, okay, that means if you calculate the df dz, you can have this answer. You also can have this answer. However, these two answers should be the same because df dz is independent of direction. Okay, so if you want to this and this is the same, you should satisfy what? Your real part here should be equal to our real part here, right? So that gives you the first equation here. Partial phi partial x equal to partial psi partial y. And we know this is equal to u, right? That's the velocity. Okay, definition of velocity potential and the stream function. And also in the imaginary part here, partial psi partial x, okay, will be equal to this partial phi partial y times minus sign here. So partial psi partial y will be equal to minus partial phi partial psi partial x. Partial phi partial y will be equal to minus partial psi partial x. And as you know, this is equal to v here. Okay, because definition of velocity potential and the stream function will be all. So that means, okay, under this kind of constraint or condition, we call this is a Cauchy-Riemann equation. Okay, it's in a complex variable. Okay, if you study the mathematics, okay, in the complex variable, you will mention about this Cauchy-Riemann equation. So once you satisfy this Cauchy-Riemann equation, okay, our df dz, okay, when you evaluate this df dz, it will be independent of the direction. Okay, you can calculate this derivative from any direction. You should be all the same. Okay, now, and if this is satisfied, we call this fz is an analytical function. Okay, that's a definition of the analytical function. Okay, and then you also can do that. Okay, you can see if you calculate, you can get this one here. Okay, they also have the so-called compatibility required like this. Okay, and this one is what? This one is you can derive this. Okay, and this one give you the Laplace psi equal to 0, and this one give you the Laplace phi equal to 0. Okay, what I did is very simple because you can see here, this is also this equal to this equal to 0. What does it mean? Because I take a partial square psi partial x partial y, and this is the same thing, but the only difference is I take this partial phi partial x first, and this partial phi partial y first, and later get a partial x here, partial y here. Right? This should be the same, right? If it just the order is different, the derivative order. So this should be equal to 0. Okay, mathematically. However, if you change the partial phi partial x to according to your Cauchy-Riemann equation, you can get this. So you also have to satisfy our stream function Laplace equal to 0, as well as our velocity potential. Okay, so all this is okay, just the same. Okay, so definition for the analytical function fz. Okay, so our real part is a very velocity potential, right? And the imaginary part is our stream function. Okay, so in the potential flow, when we define this, as you can see here, okay, this is the analytical function because, as you know, our Laplace phi will equal to 0. That's our carbon equation. Laplace phi will be equal to 0 is another carbon equation if you represent by the stream function. Okay, so this is within our equation. This is our carbon equation. So if you define like this fz will be okay automatically satisfy our analytical function. Okay, so here we define our complex potential by define like this way, and we all prove through all this argument here. We can prove, okay, this complex potential is an analytical function. Okay， 也就是说，如果说我们把这个定义成这样子的话，这是 velocity potential 是 stream function， 把它定义一个 complex potential。这个 complex potential 由这些论点来看的话，这个 complex potential 就是一个 analytical function。Okay， 从 potential flow 观点。Okay, so once you have this, okay, understanding here, okay, we also can define so-called complex velocity. Okay, and how do you calculate complex velocity? Very easy. Just take a derivative of the df dz is your complex velocity. Okay, so here again we can derive. Okay, df dz we just argument, right? We just have argument here. Df dz should be independent of direction. So any direction you calculate that this derivative should be the same. Okay, so you can df dz give you the velocity, complex velocity. Okay, so this is this fz equal to phi plus I psi here. Okay, that's our complex potential. So here we can dz here is since it's independent of direction. So we can calculate from what? Any direction. For example, we can calculate this dz from the x direction. So it becomes partial phi partial x plus I partial psi partial x. Right? It's because this f is what? Is an analytical function. 它是个可解析的一个函数。中文来讲的话，在复数函数里面，它可以解析，就表示它微分的时候可以不去计算它的方向，任何方向的微分它都会一样。无论你这个方向、这个方向，任何方向什么微分都会一样，这叫 analytical function。OK， 数学上是这样。所以我们从 x we can direct it from derivative from x direction. As you can see, partial phi partial x equal to u, partial psi partial x equal to minus v. Okay, so this complex potential will be equal to what? U minus IV. Okay, if you take a derivative of our complex potential, give you the complex velocity, and this compressed velocity will be this. Okay. And then if you using the polar coordinate, 如果说你用的是所谓极坐标 polar coordinate, dz will be equal to ei theta dr, for example. Okay. So here we have so if you calculate the polar coordinate compressed velocity like this, you can end up with like this formula here. As you can see, you can get ur minus iu theta and times exponential I minus I theta. So this sometimes when we using the polar coordinate, you have to remember this because there's additional term here, exponential minus I theta here. Okay, so here we have the compressed velocity equal to u minus iv, or in polar coordinates, ur minus iu theta times exponential minus I theta, right? That's according to here and here. And you can also define the compressed conjugate, right, of our compressed velocity. Compressed conjugate, w bar here, okay, equal to u plus iv, because the compressed conjugate just change the imaginary part sign, okay, the sign of the imaginary. So this is minus sign here, we should change it to positive sign here. Similar here, okay. So this is our compressed conjugate. So if you tie our compressed velocity with its own compressed conjugate here, you can see this is u squared plus v squared, and this become u r squared plus u theta squared, give you the magnitude, okay, square of your velocity. Okay, this give you the magnitude of, if you take a square root of this, give you the magnitude of velocity, right? 速度的大小 ，okay， 这是速度的大小的平方。So that will be equal to your v dot v, because v dot v becomes scalar, right? Scalar is our compressed is our velocity magnitude square, and also equal to gradient v dot gradient v, because our velocity is equal to gradient v here. Okay, so this is always a little bit mathematic with, okay, definition, okay, and also some definition will relate to our potential flow definition, okay, and you can combine together, give you a very good, okay. So once we have this, okay, we will go into some more basic flow, okay, 基本流场, okay. Here we have a basic flow called uniform flow. Uniform flow, when you have a flow uniformly flowing inside this flow field. For example, for this case, we have uniform flow in from the left-hand side to the right-hand side with all the same velocity. Okay, that's one kind of basic flow. When you have a flow over something, you have a uniform flow. Okay, it start with. So uniform flow in x direction give you what? U is equal to this v, right? V is this magnitude of this velocity. And since in the horizontal direction we don't have, in the vertical direction velocity we don't have any, right? So v is equal to 0. Okay. So if you do that, you can find out your compressed potential Fz for this uniform velocity in x direction will be equal to Vz. Okay, equal to Vz. And you can check. How do you check? You just take a derivative of this, give you what? Give you the compressed velocity, right? And compressed velocity, when you do the derivative here, this z, okay, you take a derivative with df dz, you get the v, and v equal to u minus iv, and this real part equal to this is this equation. And imaginary part, we don't have any imaginary part here, so this imaginary part is equal to 0. Okay, this is how you check. Okay, this will be equal to this. So for this potential field, this compressed potential, it represents this velocity field. Okay， 就如果说你要得到一个平行流的流场，这就是它的 compressed potential. If you are vertical direction, okay, flow is from, okay, upward direction, and here is your, okay, compressed potential look like. Okay, you can check that. Okay, you can see if you I minus ivz, okay, and take a derivative, give you this, and this equal to this our compressed velocity, and we can also conclude u is equal to 0, v is equal to our, okay, upward velocity v, will represent this velocity field. Okay, if you have a small angle, take alpha, okay, for this kind of flow, okay, you can also generalize this equation. Our complex velocity will be, complex potential will be equal to this. Fz is equal to, f function of z will be equal to v is potential minus IR alpha times z. You can check, okay, by take a derivative, by get the complex velocity. This is our complex velocity. By using the df dz, you can calculate this. Equal to u minus iv, and this u will be equal to this. Okay, it will be, for this flow field is like this, and v is equal to v sine alpha. Okay, so that will represent, okay, this velocity field. Okay, so we will go through a lot of basic flow. Okay, this is uniform flow, and here we have the so-called source and sink. Okay, source and sink flow. And what's that mean? The source. Source means you have a flow flowing out from one point. You flow outward. Okay. So this is all the flow. Okay, all from this source, and this source will be flow out and along this radial direction. OK， 就是当中间有一点是我们称为 source 的话，这个从这个原点开始，它会从这个点流出来，都往外流，往四。OK。 So this kind of flow we call source flow. And how do you calculate out? How do you know this kind of source flow? What's the complex potential for this kind of source flow? Okay, we can. Okay, here we just check. Okay, the source flow will give you the velocity complex potential will be like this. Fz is equal to m over 2 pi natural log z. Okay, that's a source flow, okay, source, and this m is this source strength, m, okay. And how do you check this? Okay, is a source flow for this flow field or not? We can using the complex velocity here. So this z, since this coordinate is better using the polar coordinate. Okay, 这种坐标最好是用所谓的 polar coordinate. The polar coordinate z is equal to r ei theta. Okay, when you're using the polar coordinate, z is equal to r ei theta. This r and theta is two variable for your polar coordinate. So if you take this, it becomes natural log r plus I theta, right? And times m over 2 pi, and this gives you the velocity potential plus I psi. This is our stream function. So from this equation here, we know our real part. Okay, is our stream velocity potential. So velocity potential equal to this, m over 2 pi times natural log r. And our imaginary part psi here is what? Equal to this. Okay, is m over 2 pi, n over 2 pi theta. Okay, m theta over 2 pi. Okay, so here is, so if you calculate this is your velocity potential. This is your stream function, right? And it's from stream function. When stream function is equal to a constant, means it's a straight line, right? So straight line is when theta, for this equation, theta is equal to constant, is a straight line. So straight line like this. This is one of straight line. This is another straight line. So every radius direction, okay, every radial direction is a straight line. Okay, and here is what's the equipotential line? Equipotential line for this equation is r equal to constant. So r equal to constant is this dashed line here. This is all equipotential line. Okay. Okay, and velocity. Okay, we can check velocity. And when you want to know the velocity, you just take a derivative, df dz, give you the complex velocity. So if you can see here, natural log z, take a derivative, is become what? Become 1 over z, right? So this is m over 2 pi z when you take a derivative here. Okay, and z is what? Z is equal to r ei theta. And this, we take this ei theta upward, okay, in the denominator become substantial minus I theta. What I did is because I would like to change to the exact form of a polar coordinate complex velocity. Right? I would like to compare these two because since I already mentioned before, in the complex velocity for our polar coordinate, we have additional term here. It's potential minus I theta. So I would like to have this term and this term here, okay, in order to compare more clearly. Okay, so if you compare these two here, as you can see, our UR is equal to what? UR will equal to this, right? So UR will equal to m over 2 pi r. What's U theta? U theta is the imaginary part for this, but we don't have any imaginary part for this. So U theta is equal to 0. Okay? So if you can see here, our velocity, okay, only have UR velocity. This is UR velocity, right? This is UR velocity. We don't have any U theta velocity, right? Okay, so that's true for the, and this UR velocity, okay, for this source flow is equal to m over 2 pi r. Okay. Okay, and from this equation here, you also can see when r is increased, that your UR will decrease. So for UR is equal to this location, our velocity is higher. When r is this location, our velocity is lower. Okay, so let's give you from this equation, you know the velocity is decreased along the radius direction. Okay, according to this equation. And what is m? Okay, physical meaning of this m. Okay, 它的物理意义是什么？这个 m. Okay, and you can check because if you take a UR times UR, if you take a integral of this UR times RD theta, RD theta is your this direction, right? This is your arc length. This is RD theta is your arc length. So your UR times this arc length give you what? If you integrate from 0 to 2 pi, that means you integrate along this, okay, along one of circle here, okay, and that give you what? Give you the volume flow rate, right? Because the velocity times area give you the volume flow rate, and this is, so if you do that, this is your UR, okay, from our complex velocity, and m over 2 pi r times r, this r and r is cancel, and d theta integrate 0 to 2 pi, this 2 pi also cancel, give you this m. So this m is what? Is our volume flow rate. Okay, volume flow rate from the source. Okay, volume flow rate from the source. 所以它这个 m 的物理意义就是它从受出来的什么体积流率。OK， 这个意思。Okay, so once you know that, we can. So this equation is only for our source at the original location. 这个 equation, 这个 complex velocity 是 complex potential is only for source at the original position. When your source is at different location, for example at here, right? And you should change your original point here. Okay, this is a change your original point. 所以如果说你的 source 不在原点的话，对，你在另外一个 z 零点的话，对 ，source at this location, okay, your complex potential should be like this. Okay, any question here? Okay, once you know the source, reverse direction is a sink, right? So the m is become minus m here. If the m is a positive, that means flowing out, right? When this minus m become negative, negative means flowing in, right? So all the flow is along this direction and disappear at this point. So this is like a sink, okay? 它就是好像从这个地方，这个所有的流场都会集中在这一点，然后就 sink 就不见了 ，okay? So this is when you this m define your positive mean you are source, negative mean you are sink. So that's the source and sink of, okay? Okay, and circulation vortex. When you have a vortex, okay, when you have vortex, and vortex with the circulation, okay. So how do you represent this? Okay. Complex potential for the vortex with the circulation, and here is complex potential. Look like this. It's minus I gamma over 2 pi natural log z. Okay. So that's our complex potential for our vortex with circulation gamma. And how do you know this? Okay, we can check. Okay, we also can check, and the check is we can using this complex potential, and this z equal to REI theta here, and we also divide into the real imaginary part and the real part. It become like this. So we can find out our psi is what? Our psi is gamma over 2 pi theta, right? Because this theta and this I and I give you -1 times this -1 give you a positive value, that's the real part. So real part is this. Okay, 这是实部。Okay, so our psi is equal to our theta is a constant. Okay, so theta is constant is our equipotential line. And the imaginary part for this equation here, imaginary part is this part, right? This part is gamma over 2 pi natural log r times minus sign here. So this is our stream function. Okay, this is our stream function. So stream function give you, if this is stream function, when stream function equal to a constant, means it's r equal to constant because all these variables are constant. Only this is a variable r. Okay, so r is constant is our stream line. What do you mean the r is constant is our stream line? R equal to constant is what? Is this line here, right? This is different r equal to constant. This is different. So this line here give you the stream line. So this look like a vortex, right? This look like a vortex. Okay. And we also can check our velocity field. Okay. So to find out our complex velocity, we take a derivative with our complex potential df dz. So as you can see, natural log z give you the derivative give you 1 over z. Okay. So everything is the same. Only this natural log z become 1 over z. And again, we like to kind of compare with this, okay, polar coordinates, okay, complex velocity. So we should have this outside of this bracket, okay. So what we did is z replaced by ei theta here, and this ei theta, okay, take in the denominator, 把它放到分子上去 so we can compare, okay. So here, as you can see, ur is equal to what? Ur is equal to 0. We don't have any UR velocity because as you can see, this is velocity, right? Velocity is along this circular direction. We don't have any velocity in the radial direction. Right? 我们没有任何径向的速度，我们只有这些西大方向的速度。Okay, 因为它是个 vortex. Okay, and here when you compare this and this, okay, you can see U theta is equal to this, is equal to gamma over 2 pi r. So this is a velocity in the theta direction, okay, in the theta direction. So, and the gamma, this gamma here, this complex potential gamma here, is we can also prove this is a circulation before the definition of circulation. So you take a u theta r d theta, this line integral along this path give you the circulation, and if you substitute this u theta into this equation, you end up with gamma here. And this gamma is our circulation. Okay. Okay. 所以我们可以证明这个上面这个 gamma 就是我们以前所定义的 circulation. 可以吗 Okay. And for sign convention here, okay, as you can see, when the gamma is greater than 0, that's a positive counterclockwise direction. That means the vortex in this direction, in counterclockwise direction, we define our gamma is greater than 0. And if you are negative, means you are clockwise direction vortex. Okay. 对，一个是顺时针，一个是逆时针方向。对，正的话应该是逆时针方向，因为我们的 coordinate system, this is it will be like this. Theta is this direction, right? Theta is this direction usually. Okay, 我们一般的 polar coordinate 系统的话，会变成这个。Okay. So, and if you have this vortex at a different location, okay, for example, this vortex is instead of it's z equal to 0, and this vortex is z equal to z sub 0 here. Okay, and your complex potential should change like this. The difference is only z is minus 0 here. However, our location of origin of this vortex is changed to z sub 0. So our complex potential should change like this. Okay. So from here, you also can define, as you can see here, from the velocity field. Okay. Our r equal to 0 give you what? Give you u theta is infinity, right? 如果说你 r 等于0的话，你的 u theta, u sub theta here give you is infinity. That's impossible, right? So that's a singular point in mathematically. Okay? So at the origin, at z equal to, okay, your origin of your vortex here. If you have the contour enclose this